All right, here we go in our next section. This is 5.3, derivatives of a logarithmic function. This is continuing on from what we did in the previous section was derivatives of exponential functions. And so this just ends up being kind of the natural progression of that. And it starts off by reminding us, okay, so the derivative of e to the x is e to the x itself. And the derivative of b to the x is b to the x multiplied by ln b. Remember that what we were saying about the derivative of e to the x is really, this is just a special case of the derivative of b to the x, where the base is actually this special number e, 2.71828-ish. So we could just call it e to the x times ln e, but remember that natural log of e is just 1. And so this part is unnecessary, and we end up with this beautiful derivative of e to the x. It's just e to the x. Okay, so from there we now start to look at what would happen with natural log. And what's going to happen with natural log is we're going to start with the exponential form to find our derivative of natural log. So we're going to swap this around. And so maybe you can try this. Maybe you can take a couple minutes, see if you can swap this around into exponent form and see if you can take the derivative and get there. So maybe hit pause and try this for a minute where you attempt to do this one on your own. It's not too bad. So go ahead and I'll see you in a minute. All right, so if you attempted this, maybe your first step would be, all right, and we can look at this a couple of different ways. We can take this y is equal to ln x, and we can swap that around into exponent form and say that that's the equivalent of e to the y is equal to x. Really what we're doing in this step is we're raising both the left side and the right side as exponents of e. And so when we do that, here's our next step, e to the y is equal to x. That's our equivalent form. If we differentiate this, we're going to differentiate the left side. It's implicit differentiation. We do that and we get e to the y times y prime. The right side is just 1 when we differentiate that with respect to x. And then step 1 over e to the y. But if we look back at this step here, we were told, well, we surmised that e to the y is equal to x. And if e to the y is x, then let's substitute that back and let's call e to the y is x. So this ends up being our derivative of ln x. If we have natural log of x, it's 1 over x. If we have y is equal to log x base b, so this is really the generalized case of what we just did on the left. On the left, we did this logarithm of base e. It is called natural log. So if we do this in general and we call this logarithm of x base b, again, let's swap this around into exponent form, and this ends up being b to the y equal to x. We're going to do the same thing here. We're going to differentiate both sides. And when we differentiate b to the y, remember that that ends up being b to the y times the derivative of y ln b. The derivative of x is just 1. And so therefore, y prime is equal to 1 over e to the y ln b. But similar to what we just did in the previous, is b to the y is just x. So let's call it that. And we end up with this, is here's our first derivative of logarithm of x base b, and our logarithm of ln of x. So in summary, it works with not just x, but any function of x. We would just use chain rule to do this. So therefore, ln of f of x, the derivative of that, is going to be 1 over f of x. That's the natural log part. And then if we are going to chain rule this and then deal with the inside of this function, well, the inside is f of x, so the derivative of that is f prime. So by chain rule, we have 1 over f of x times f prime of x. There's your derivative of ln f of x. Last lesson, we also looked at this, y is equal to b to the f of x. So we have this base of b raised to another exponent. So b to the f of x is our first piece, times ln b, because it's a base other than e. If it's a base other than e, we have this factor of ln b, and then multiplied, again, chain rule, is multiplying by f prime of x, is our last step. And then our last one that we have here, logarithm of f of x is 1 over f of x ln b. The 1 over f of x is the fact that we have logarithm, and we're taking the derivative of a log. The fact that it's base b is this part, so we have to kick out this ln b in the denominator here. Remember that that's in the denominator. And then by chain rule, we also have this factor of f prime of x. All right, so when we go ahead and we're going to start differentiating some of these. Natural log of 2x cubed, derivative of this. All right. So therefore, dy dx, you could call it y prime if you like. So natural log, so 1 over 2x cubed. 1 over 2x cubed, because it's a natural log, we don't have the ln e component. And then we're going to multiply by the derivative of that inner function. And that derivative of the inner function is 6x squared. We simplify this, it ends up being 3 over x. 2, natural log of x, ln x times x squared. So we have product rule. Derivative of the first is 1 over x times x squared plus ln x times 2x. And of course, we can simplify this a little bit, and we could call this x plus 2x ln x. Number 3. So it looks like we have some quotient rule and we have chain rule going on here. Natural log of tan of x divided by x. So therefore, dy dx is equal to, so the derivative of the numerator is 1 over tan x times the derivative of the inside. Let's just chain rule that, ends up being secant squared x times the bottom. It's just x. We're going to subtract ln of tan x stays the same times the derivative of the bottom, which is just x. All of this is being divided by x squared. We can tidy this up a bit, and we can call this secant squared x. I'd normally put this x actually out front, and so we'd call it maybe x secant squared x, just to make it clear what we actually are dealing with there. If we have a common denominator between these first two terms, then we have minus tan x ln of tan x. And this is all being divided by tan x, and it's all being divided by x squared, so let's move that. Tan x. X secant squared x minus tan x ln tan x over x squared tan x, that's it. Number 4, y is equal to 3 to the x to the 5. So we do y dx. We have a base of 3, so we write this as 3 to the x to the 5 times natural log of that base times the derivative of the exponent. Derivative of the exponent is 5 x to the 4. Doesn't really simplify from there. That's pretty much it. We could reorder it. We'll just leave it at that. That's fine too. Number 5, almost done here. 4 log of square root x base 2. This ends up being 4. All right, so the logarithm of root x base 2 is we'll take 1 over root x. But we have to have this ln 2 downstairs with it because it's not natural log, it's a logarithm of base 2, so we have that part kicking out, and then we're going to multiply it by the derivative of the inside of that function. So we're just going to chain rule that. That's 1/2. We can tidy this up a bit, and we can call this 4 over 2. We've got root x. We've got another root x. We've got ln 2 downstairs. This tidies up some more. A lot, actually. 2 over x ln 2. Beautiful. You know what's not beautiful? This next one. So this one's going to be a little messy. We're going to have to just go slowly through this and make sure that we're keeping track of everything that we're taking derivatives of. We've got y squared on the left side. We do have some y over on the right side, so we have some implicit differentiation. We take the derivative of y squared with respect to x, and this ends up being, no, I don't want that. I want 2y. I'm going to write this as y prime instead of dy dx, just to make this look a little tidier. Okay, so natural log of x cubed minus y. Natural log means we're going to take 1 over x cubed minus y. And then we're going to multiply this by the derivative of x cubed minus y. So it's just going to be multiplied by 3x squared minus y prime. It doesn't look that bad, but we're going to need to distribute this. We're going to need to distribute this 1 over x cubed minus y into this bracket because we're going to have to collect our y primes on the left side eventually. Let's leave this as 2y y prime is equal to 3x squared over x cubed minus y minus y prime over x cubed minus y. We're going to add that to both sides. 2y y prime minus y prime over x cubed minus y is equal to 3x squared over x cubed minus y. So a little bit ugly. We're going to need a common denominator on the left side before we factor away your y prime. So this ends up being, this is y prime, 2y x cubed minus y minus 1 over x cubed minus y. So I've common factored y prime on the left side, and I also made a common denominator with this term, the 2y prime over 1, multiplied it up and down by x cubed minus y. This is all equal to, the right side is no change, 3x squared. 3x squared over x cubed minus y. We're now going to multiply both sides by the reciprocal of the left. We're going to multiply both sides by x cubed minus y, and we're going to divide it by 2y x cubed minus y minus 1. It leaves us with 3x squared upstairs, 2y x cubed minus y minus 1 downstairs. And that is it. All right. Good luck, guys. And if you have any questions, please ask.